So by now you should have done your structural diagram. Okay, so let's think about what we are seeing here in terms of formations. So I think we're going to start maybe looking at the stratigraphic columns that are given on the sides of the map, because they are very useful in the sense that they are to scale. So you can see that everything that is here on the left and to the right, it's 1 inch to 500 feet. I'm not going to make the conversion right now. I'm going to let you do the conversion, but that means that for each of the units here, you can constrain the thickness, the maximum thickness that your unit is going to have on your cross section. So that's very useful. In terms of the units, we can see, okay, very little on the map that is exposed that is pre-old red sandstone. So we're starting in the old red sandstone here with essentially sandstones. And then we get, so these are the gray units that we find in our area essentially here. And then we get into these blue units that are carboniferous. And pretty much most of the stratigraphic series here is carboniferous. So we've got huge amount of carboniferous. We're talking about kilometers of carboniferous that have been deposited here. And they're all sedimentary rocks. So we have a sedimentary environment, and we've got, during the Carboniferous, huge successions that are being deposited. What we can see is that roughly what is in the blue is this limestone series. And then we get into these coal measures, lower coal measure, upper coal measures, and then here more upper coal measures. So we've got an environment that is where we've got a lot of sediment and organic matter which is actively being deposited here during the Carboniferous. What we have then is a gap here, and you can see that at the end of this Carboniferous we've got a gap, a nonconformity, and we get in the Triassic. So the Permian is missing, and we've got a big change in the environment, and that's something that you can probably see when you start looking at the structure. In terms of structure, something that is striking is when you look at the pre-Triassic units, essentially these blue units, is the folding. So you've got a series of folds with the axes that are like roughly east-west. You can see this fold axis, and you can see that through the repetition of the units on both sides and through the dips of the bed. So here you can see we're dipping around 20-30 degrees to the south. Here we're dipping around 60-70 degrees to the north. So we've got an anticline here, a syncline here that we don't see so well, another anticline here, and like an anticline here and a syncline here. So we've got a series of fairly tight folds that characterize these units that predate the Triassic. We can also see that we've got a series of folds that seems to have orientation that roughly align with the folds themselves. So we've got a series of thrusts. You can see the cleft down thrust here. You can see here there is a thrust here. We will get back to that in a minute, but everything here seems to be consistent with a phase of compression, north-south compression, that form this anticline and syncline, and potentially some of this thrust. Okay, so how do we get the dip of a fault typically when we've got a geological map? Well, we look at how the trace of the fault interacts with the topography. The problem on this map is that, well, first we don't really see the topography very well, and you will thank me for giving you a topographic profile. It's been quite challenging to do the topographic profile along this line. But the other reason why we don't see the topography very well is because there's not much topography, there's not much relief. Like the elevations are in feet, and we can see here we've got a summit that is at 765 feet. We just have a few hundreds of meters of relief. So we are in an area, it's not big mountains and deep valley, it's essentially rolling hills and broad valleys. So it's very difficult actually to get a sense of whether the faults are dipping steeply or not by looking at how they interact with the topography. We will see how we infer that from later when we get into the structure. So faults and folds associated with a north-south compression seems to characterize the pre-Triassic units, and then we get we get into the Triassic. And we've got a change of environment here, because what we can see is that it's essentially conglomerates and some marls. So we have something that looks a bit more continental. Most of the, what we've got here, we had limestones in the Carboniferous. And then we get into an environment where we've got conglomerates and sandstones and marls. So we are possibly in a more continental environment. What is striking between the Triassic and what predates the Triassic is that we've got a very strong angular unconformity, and you can see it very well here. Like the contact is highly contorted. Here we can see that all over the place. So what I'd like you to do now is think about, okay, we are in these landscapes, we've got these anticlines, we've got the syncline. Try to think about where this Triassic is being deposited, where the conglomerates are being deposited, because I think it's interesting to look at how they relate to the overall structure and morphology, and think also about how this compares to the Quaternary. So we can see that in yellow here we've got Quaternary, which is quite extensive all over this map. So it's Quaternary, essentially alluvial sediments that are being brought by the river. So that was just my masterpiece. That's my structural diagram with the Severn estuary here. We've got the river, we've got Bristol here, we've got a big river, and we've got a series of thrust, a series of faults. In blue, I try to represent here what is the Triassic, essentially, and then in green, we've got the Quaternary. So Quaternary sediment, Triassic conglomerate, and marls, and then we've got in white here that old red sandstone to Carboniferous folded sedimentary succession with the folds axis indicated on this map. Okay, so think about the Triassic now.